Okay, here's a diagram that depicts the situation. We've got this wall, 10 feet high. It's 2 feet from this building. We don't know how tall the building is. It really doesn't matter. And we want to know what is the length of the shortest ladder that will reach from leaning against the building across the top of the wall and, of course, hit the ground. And we're going to do this depending on the angle theta right here. And one thing to notice is that if you draw this dashed line right here, that both of these angles will be angle theta because we've got two parallel lines cut by the red transversal, and corresponding angles are congruent. So we can set up, first of all, the length of the ladder using these letters P, B, and Q is PB plus BQ. And then we can recognize that using this little triangle right here, BP is the secant of theta is equal to BP over 2. Because secant is the inverse of cosine. So the reciprocal of cosine. And in this triangle down here, the cosecant of theta is BQ, this part of the ladder, over 10. So I can use these two relationships to rewrite and come up with a function for L depending on theta. L of theta, the length of the ladder, is equal to 2 secant theta, I solve for BP, plus 10 cosecant theta. We might make note of the fact what happens when theta is equal to 0 or theta is equal to 90. We'll see this subsequently, that at the endpoints of this interval where theta has to be between 0 and 90 degrees, that the ladder is not short at the boundary points. So we're only going to look for the critical numbers for L, which means find the first derivative and set it equal to 0. So L prime is equal to the derivative of the secant theta is secant tangent. The derivative of cosecant is negative cosecant cotangent. We want to know, when does this equal 0? So there's the equation. Probably a good idea to convert to sines and cosines to see what happens. And I transpose this term to the right side of the equal sign, converting to sines and cosines. Realize that if I divide both sides by 2, I'll get a 5 on the right. If I divide both sides by this coefficient of 10, multiplying these denominators together, this is what I get. Multiply the numerator by the reciprocal of the denominator is one way to think about it. I get sine cubed over cosine cubed, which is tangent cubed. So to solve for theta, take the cube root of both sides, the cube root of 5. Theta is equal to the inverse tangent of the cube root of 5, or the angle that has a tangent of the cube root of 5. So if I go to board 2, there's my original function. If I substitute or find L of the angle that has a tangent of the cube root of 5, this is what it would look like. And if I use a calculator to find that, there's theta, the angle that has a tangent of the cube root of 5. Looks like it's 59 degrees. And then if I substitute that into this function, which I'm using M for maximum, I should have used, M for minimum. If I put different values of theta in here for X, this table shows what happens. See, it's 0 and 90 were undefined. So the shortest ladder, well, you can see if I substitute different values of theta in here other than theta sub 2, the angle that has a tangent of the cube root of 5, I get longer ladders. So this definitely is the shortest ladder that reaches over that wall. If I share my screen and go to Desmos just so you can see what's happening. Here it is, right here. So right now, theta equal to 55 degrees. The length of this ladder is 15.69. I said make max here. I should have said make minimum. I want the minimum ladder. There it is right there. Okay, so if I change theta, the length of that ladder changes until it gets really big. The closer you get to 90 degrees. If I make it a minimum, happens at 59.68 degrees. And that length of the ladder is 15.54. 55. There you go. Hope that helped. If you have any questions, post a comment.